Hi, my name is Amy Sullivan, and I'm the chair of the AAAR Endowment Committee. It's my pleasure to welcome you to the 16th in our monthly series of AS&T lectures. This is a new initiative for AAAR being supported by the Freelander Memorial Fund. So each month, one of the editors of AS&T pick a high impact paper to be presented by its authors. With these lectures, we hope to be able to highlight the amazing research happening in our community, to be able to gather together outside of the annual conference, and also to tie our journal to other activities. So these lectures are being recorded and will be posted later to AAAR's YouTube channel, which you can access from the AAAR website under the events tab. In addition, each month, one of our student chapters is serving as host. And so I want to thank everyone who's helped to make these lectures possible and for all of you for joining us. And with that, I'll turn it over to our student chapter from Colorado State University to get us started. Thanks.
Cool. Thanks, Amy. Yeah, my name is Sam O'Donnell, and I'm at Colorado State University, and I'm going to be introducing our speaker today. So Eric completed his bachelor's in applied science at the University of Manitoba in Canada in 2015. He then completed his master's in applied science at the University of Victoria in Canada in 2017, and is now in his last semester of his PhD at the University of California, Berkeley. During his PhD, he is focused on the experimental study of dispersed multi-phase flows through the context of two main projects. The first of which is the transport and deposition of droplets ejected via cough, and the second is the effect of bubble transport on the shedding frequency of a cylinder in a cross flow. And so with that, I will hand it over to you, Eric. And I think you're planning on giving about a 45-minute talk, and then we should leave 15 minutes at the end for questions. So, all right, take it away.
Perfect. Thanks for the introduction. And yeah, thanks for being here. I'm excited to share this work with you all. And the main focus of the talk is going to be on this paper. So droplet and particle methods to investigate turbulent particle-laden jets. The sort of general structure of the talk is just going to be a sort of motivation for why we think it's necessary to develop different methods to study sort of transport and deposition of particles and droplets, and then go into some of the key results of the paper. And if we have time, then hopefully discussing some results that we had in a paper published earlier this year in AS&T as well, in which we sort of use some of these methods in a slightly different application. During the talk, if you have any questions, then yeah, don't hesitate to ask. Yeah, it definitely doesn't need to be that formal. So without further ado, so just to dive into it, so basically, why do we care? And I think that should be pretty obvious to most people. But I mean, the biggest motivation, right, is just the spread of COVID. And specifically, what I want to highlight is the fact that COVID spreads differently in different regions, different environments, and under different rules. So, you know, there's not the same spreading happening everywhere. There's clearly an environmental effect on, you know, how readily COVID spreads. And, you know, it's important to understand how that happens. And basically the first step of doing so is, you know, how do droplets spread? How does like the moment somebody coughs, how does that droplet get transported around the room and then potentially infect somebody else? So I took this from a paper from Lydia Berubia in 2021, and I think it does a great job of highlighting how sort of disease transmission is just a fundamentally, it's a fluid mechanics problem. And there's so many different aspects of fluid mechanics that sort of are critical to each segment of the transport from the infectious host to the new host. And it's not all aspects are, you know, readily studied. Not all aspects are well known, even a little bit. And, you know, it's really a good opportunity for us to sort of get in there and make a contribution where hopefully we can, specifically, we want to look at this segment of it, which is just the link between the environment and the sort of emission and transport of droplets. So basically what we want to focus on is the moment of sort of like a droplet being expelled from somebody to landing on a new surface. And how do you study that? How are there methods for studying that? And what we found was just that there weren't any sort of really well-known methods, well-proven methods. So we felt like it was necessary to kind of put our contribution out there and then apply those in some test cases. Not saying that obviously there's lots of other problems. There's so many other avenues of research here. This is just the particular one that we decided to focus on. So beginning with the sort of most basic case. So just you have a droplet in some environment, right? And it has initial height, it has initial diameter, and you just want to know where does it go, right? Specifically, if you want to determine like a social distance, for example, then how far is that droplet going to move? And how far away would you need to be safe, right? Is it 6 feet? Is it more? Is it less? And just studying the motion of that droplet, what sort of environmental factors are at play to determine how far that it goes? And one of the main factors is that there's a sort of big temperature and humidity aspect. So basically the general path of a droplet once it gets expelled is that it's going to shrink to some equilibrium size and then be deposited. And the rate at which it shrinks is dependent on the humidity. So, even if you have the same droplet expelled with the same initial diameter, the same initial height, if it's in a dry environment, it might shrink to its equilibrium size and then fly quite far, depending on the sort of background flow in the environment. Or it might, in a high humidity environment, stay quite large and might actually hit the surface before it's shrunk to its equilibrium size. So basically how far the droplet travels depends on how fast it evaporates, and how fast it evaporates depends on the humidity in the room. So you can already see that, the environment is definitely going to have a big impact. One quick note that I want to make here is that, yes, the droplet in theory could evaporate to nothing, but in practice doesn't, because there's just other compounds present. Saliva is not just pure water. So the good news is that, a lot of this has been studied previously, at least at a fundamental level. And I want to give a quick introduction to that, which is basically that if we consider this pioneering study by Wells in 1934, basically, if you're wanting to figure out how far a droplet moves, the first step is to sort of assess these two different time scales that Wells thought were really important and definitely are important. And that's the first time scale is the fall in time, basically how long it takes for a droplet to hit the ground. And he was studying from a height of 2 meters, so human-ish height. And then the second time scale is how fast that droplet evaporates. So basically, if you have a large droplet, it's going to hit the ground before it's evaporated to its equilibrium size. Alternatively, if you have a small droplet, it'll evaporate much more quickly, and it will, it won't have hit the ground when it's sort of reached its equilibrium size, which is much smaller than its initial size. And as a result, it'll be, more difficult to determine where it ends up because, it'll respond more readily to, background flows present in the room. But that's not the full story. The full story is that, or at least part of the story, is that you have humidity, right, which affects the evaporation rate. So essentially that time scale of evaporation is dependent on the environment. And that's, you're gonna, in humid air, then it'll evaporate more slowly. In dry air, it'll evaporate more quickly. And, if the sort of general idea that came out of this was that you had this critical droplet size, which is about 100 microns, and that if you were in a humid room, then that would be a droplet that would evaporate at about the same, it would take about the same amount of time to evaporate as it would take to hit the ground from 2 meters. So what that meant was that you had these two sort of schools of thought in terms of droplet dynamics, which was that you have aerosols, which are, smaller than this critical size, which shrink to an equilibrium size before they deposit, versus ballistic droplets, which deposit before they can shrink to an equilibrium size. So you can kind of think of them as like cannonballs, basically, that, they get ejected from the mouth and then they hit the surface as they're still evaporating. So again, the sort of characterization between aerosols and ballistic droplets kind of persisted for a long time is still sort of present in the literature today. And there's at least some reason to think that the CDC's original sort of 3 to 6 foot social distancing guideline originated from this work. Kind of, maybe it's a guideline used to sort of separate yourself from ballistic droplets. However, is this a complete picture? And I would argue probably not. And I think the reason for that, right, is that, if let's say you're a sufficiently large droplet that you're going to deposit before it's sort of evaporated to its equilibrium size, then is 6 feet always good enough? No, and there's a bunch of different reasons for that. The first of which is that the sort of dynamics of how a droplet is expelled from somebody is not, in isolation, right? The droplet just isn't, it's not just one droplet in the room. The droplets are actually part of this sort of multi-phase turbulent puff. And I've cited another paper by Lydia Berubia here, which I think is really good. It really goes into this in detail. But basically, when you have this multi-phase turbulent puff, you have variable local humidity, and in turn, you have variable evaporation rates. So depending on where the droplet is in the puff, it will evaporate to an equilibrium size at different rates. And it sort of develops this complex interaction between the puff and the environment to determine how far droplets are expelled. And that, again, that isn't just the local evaporation rate, it's the fact that when a droplet is contained within a puff, it's going to be carried forward with that sort of inertia of the carrier gas, which means it has reduced drag compared to being expelled just into a perfectly quiescent environment. So droplets can actually go much further than you'd expect them to be able to if you consider them in isolation. But again, is this a complete picture? No, I still don't think it's a complete picture. And the reason is because we're still neglecting some environmental factors. So it's, even despite this sort of additional complexity and accounting for the fact that it's a multi-phase turbulent puff, you could still have a wind behind you. You could still have thermal gradients, which are going to kind of mix the air. You could still have walls. And all of that means to say that it's very difficult to predict exactly where a droplet is going to go when it exits your mouth. But it's also very important to know where it goes, because we need to know that in order to determine what guidelines are appropriate to, protect against COVID or other diseases. So as a general sort of motivation for the talk, just a couple sort of rhetorical questions is, do you really think that 6 feet is good enough in all conditions? I'd argue probably not, because if I have a fan blowing behind me, the droplets that I expel are likely going to go a lot further than they would otherwise. And then the second question is it possible to experimentally test all of those situations? Definitely not, right? I mean, we can study some cases, but for the most part, I think a lot of the direction that at least I see this going in is that we need accurate numerical tools to study droplet transport in different environments, which basically means that we need to develop high quality validation experiments in order to make sure that we can predict where droplets are going to go when you start accounting for all those different factors that I mentioned, which is the interaction of the sort of multi-phase puff you eject with the environment, and then, or if you add sort of strong preferential flows in the room like wind or something else, or thermal gradients or walls or any of these other effects. So hopefully that's a good motivation going into this paper. So basically, given that we need to develop these high quality sort of validation experiments, then we need to develop some methods for doing that. So hence, hopefully our work is going to make a contribution towards that, specifically looking at how we might study the sort of droplet and particle transport and deposition onto different surfaces. So for the talk today, I want to begin with some theory, then I'll go to a description of the laboratory facility, a description of the methods that we developed that are covered in the paper, a sort of application of those methods, comparison to CFD, also covered in the paper. And then hopefully, if there's time, I'll go into this sort of second paper we published earlier this year, where we showed this applied again to a more realistic mouth geometry. So again, I just want to reiterate, if at any point you have any questions, then please let me know. I'll try to stop periodically throughout the talk to see if there's any questions. And then you can just put them in chat or raise your hand. All right, so the theoretical background. So again, I've hopefully motivated that droplets move differently in different environments, and that we want to develop validation tools so that we can study this numerically. But what does validation really mean? Basically, why is it necessary? Why is it so hard to validate this? Because again, F equals ma in and of itself is not that hard of an equation, right? I mean, it's simple to write. Why is it so challenging? Why is validation necessary? Basically, what we mean by validation is, can we determine what terms are most critical to include in droplet transport models, what resolution is required in the numerical scheme to solve these equations accurately. And again, hopefully in the next couple slides, I'll go into why this equation becomes so challenging and why it's necessary to drop some of these terms in order to make the problem tractable if we want to solve it numerically. So we start with this equation. If we just look at a solid sphere, so we're not considering evaporation, then there's some body forces and some surface forces. The body forces I'm giving here are the force due to gravity. I'm also including some electrostatic forces, which typically I would have thought could be neglected, but as I'll go in later in the talk, sometimes sort of show up in really annoying and unexpected ways. And then the surface forces, basically you have the force of the undisturbed flow, which you could kind of think of as just being like if you had an infinitely small particle that was the same density as the fluid and moving exactly the speed of the fluid, then it would still move with the fluid, but it wouldn't disturb the flow at all. Okay, yeah, I'm just seeing a question in the chat. The growth is only about 10%, basically the effective humidity. And I see there's a raised hand as well, and I'll get to you as well. Yes, so basically, when you're studying deposition, is relative humidity important? Yes, I understand that, depending on how many, like sort of what compounds are included in that droplet, that equilibrium size might not change that much in different humidities, right? I mean, you can imagine the sort of most extreme case where it was pure water and, it would evaporate completely versus, a true saliva where it would evaporate less and have the equilibrium size would be potentially closer to the initial size. So yeah, what I don't want to say for sure is I don't want to make any comment that specifically for COVID, what effect relative humidity has. I'm basically arguing that it's an effect that we need to consider, and we need validation experiments to sort of prove in different situations whether it's important or not. And specifically, my work is basically studying, once the droplet gets expelled, what will happen to it. And we're not looking at the sort of composition of that droplet. We're only going to be looking at liquid droplets with fluorescein. And the uptake of the virus, again, really important. Let me just skip back to this first slide. And I just want to make sure that I'm clear about what I'll be talking today and what I won't be talking about today. Yes, there's lots of different stages in this process from an infectious host to a new host, including the uptake of the virus in the droplets, where the droplets are expelled, what the size distributions are that are being produced. We're not considering that. We're basically just considering the moment the droplets get expelled to the point that they land on the surface. So nothing to do with the actual uptake of virus in the original droplets, and nothing to do with the infection once the droplets land on something else. Now I think I can take a question. Modi, if you want to unmute yourself. All right, I'll proceed, but if you if you want to put your question in chat, then feel free. All right, so basically where I was at was that basically there's some force from the undisturbed flow and there's force from the disturbed flow, which is basically these additional terms like added mass, drag, basket history force, lift, all which arise from the fact that when the sphere moves through the fluid, again, we're not considering evaporation in this equation yet, then it's gonna alter the forces experienced by the sphere. And notably, we also don't account for particle-particle interactions. So, a sort of general modeling approach that we might have is that we take this equation, we compute the forces on the particle, basically everything on the right-hand side, and we integrate the particle position in time, and we basically allow us to determine, okay, how does that particle move forward, and what trajectory does it take? Well, this could be computationally intensive. Do we expect this to return accurate particle positions? Let's dive a little deeper. So basically, what are those actual terms that I'm just giving right now? So for one-way coupled flow, those terms are still quite complicated. So basically, again, we have the force of the undisturbed fluid, we have drag, then we have added mass, which is basically the fact that that sphere needs to accelerate the fluid around it as it moves through the fluid. We have the basket history force, which again is the fact that the sort of boundary layer development on that sphere is a function of time. So if there's large accelerations, then that's going to change how the rate at which that boundary layer develops, which could affect the forces. So again, if you have large accelerations, then this term becomes important. We have Safman lift, which is basically lift induced from velocity gradients present in the fluid, or Magnus lift, which is lift induced from rotations of the particle in the fluid. And again, you can see that this is for just one-way coupled flow. So basically, no particle-particle interactions. The effect of the sphere on the fluid is very small. And it still becomes quite a complicated equation, but let's again take a look specifically at some terms of this equation to see why this becomes challenging to model. The first piece of this is that nearly every term has a factor associated with it, and this is generally Reynolds number dependent. And you need to account for this to have an accurate model, which is basically you need to know how this factor changes with Reynolds number and compute as your Reynolds number changes in your simulation, these new factors potentially, depending on the variation of Reynolds number in your simulation. We'd also need to actually know the exact undisturbed flow field to compute all of these terms accurately, which is very challenging. And lastly, the sort of killer here is that to truly compute this equation accurately, we actually need to integrate from the start of time, which is just impossible. So basically, no matter how we cut it, this is always going to be an approximation. And again, we haven't even counted for evaporation. So essentially, this is again a sort of motivation for why you need these validation experiments, because you need to make necessary approximations to compute the trajectory of a droplet or a particle, at least in this case, in order to compute those positions accurately. And okay, another question, chat: what conditions make these other forces important? It's a great question, and one that I won't get into here just because there's a lot more material to cover. It basically depends largely on the type of flow that you have. If you, like I mentioned for the basket history force, for example, that becomes important when you have large accelerations. If your particles are sufficiently small and they're moving, so basically like their inertia is very low. So basically, let's say the density of the particle is close to that of the carrier fluid. The particles are small, so you don't have as many finite size problems. Then you can start to neglect some additional terms because you're sort of in the Stokes flow regime, which means that you could, you could neglect your lift. You could, neglect your basket history force, and this equation becomes a lot more simple. But it depends on the regime in which you're operating. And what I want to focus on today is basically methods to go about conducting experiments to determine that exact point, right? What terms can you compute and which terms can you neglect? But I will, to continue, basically, again, there's some key problems that I've basically just summarized. Yeah, hopefully motivating that why we need high quality validation experiments. And yeah, again, to kind of answer this question a slight bit more detail, how can you determine which terms can be neglected? Because we can't really turn off physics, or can we, I guess. We can eject solid particles, so there's no evaporation. We can eliminate electrical fields, so you can neglect terms that way. We can, and then, sort of most importantly, we can study particle motion in canonical flows, which are well understood. And they basically allow us to know the flow field with reasonable accuracy, and we can have confidence in eliminating certain terms. So again, it depends on the particular flow you're dealing with, but for example, small fluid accelerations, you can neglect your history flows. So basically, the methods that we want to develop is we want to study canonical, well-known flows, which requires a controlled facility, and we want to study both solid particles and liquid droplets, both of which need their own approaches. So to dive into the facility, basically where we conducted the experiments was a converted walk-in freezer. So why we did that was because we want to conduct experiments on room scale, but we want to control the environment as much as possible. So this is about it's a 3.75 meter by 2.3 by 2 meter cube that only has a handful of entry points for flow. Basically, that's to inject the flows that we want, and then one pressure release hole. And the main features of this is that it's isothermal, because we found that even small temperature gradients were enough to set up a sort of detectable flow which could influence motion of the particles. It's quiescent, so there's no additional flows. Size of potential, and basically we only want the flow that we generate. Essentially, the reason is because we want, when I gave the equation, right, it's really important to compute those terms to know the flow field accurately, which means that we need to study a well-known flow with very little influence from additional sources like thermal gradients, or like if you turn on the AC, for example, and it just has a slow circulation in the room. So, and then basically the next step of the paper is then applying this to study droplets. So recall that, again, what I want to highlight earlier was that we're studying the moment of droplet expulsion to landing on a new surface. So we're not studying how sort of virus uptake or anything like that. We're just studying specifically, okay, if you have a droplet of a particular size, let's develop some methods that allow you to determine where that droplet ends up. And basically this involved 3 key steps. So essentially, how do you generate the droplets? How do you size the droplets that you generate? Because obviously that's a really important factor. And then how do you determine where they end up? I want to add this disclaimer here that we have some brief results that we showed in the paper. We were planning to publish an additional paper with a lot more results, but unfortunately, due to other sort of funding and research priorities, we weren't able to conduct those experiments. But hopefully somebody in our lab or somebody listening potentially in the audience can use our methods to make that validation data set, because I think it's really important and really unfortunate that I'm not able to present more results today. Basically what we did though is that, there's many different ways to produce droplets. You can use, a commercial humidifier is one of the easiest ways, and what we use, and then we can size the droplets produced using that humidifier using a phase Doppler interferometer, which basically has 2 intersecting laser beams. As droplets pass through that intersection point, they create a series of interference fringes. And basically by studying that fringe pattern, you can determine what size droplets pass through the intersection point. That being said, though, generally the more monospersed the droplets are, the better, and I'll go into that in a little bit of detail. So the plan is to conduct experiments with the sort of monodispersed TSI flow focusing generator, but unfortunately we didn't get a chance to do that. So now that we have a way of sizing the droplets, generating the droplets, let's determine where they deposit. And how we chose to do that was that we generate droplets with a dilute concentration of water and fluorescein dye. And then we place little wayboats, basically like little squares around the room. And as droplets were expelled into the room, then they would settle out at different locations. some of them would land in these weigh boats. And basically, as they dry, they deposit the fluorescent salt inside the weigh boat. And then we basically rinse the weigh boats with a known quantity of water, creating this little concentration, which then we can measure with a fluorometer and determine how much fluorescent salt is actually deposited in that weigh boat. And you can see that there's, the limit of the particular fluorometer used is 10 parts per billion, which is really incredible because it allows us to determine, even a small quantity of droplets that were deposited. By analyzing the concentration of fluorescein in each weigh boat, you could determine the total amount of fluorescein that was deposited. Basically, by studying the total fluorescein, you could estimate the number of droplets using the inlet droplet histogram. And that's kind of what we show here, right, is that you can kind of determine this relative concentration profile of, if you eject droplets into the room, where do they typically end up? Again, a key note here, though, is that we only know the cumulative amount of fluorescein, and we're estimating the cumulative number of droplets. So basically, monospersed droplets yields cleaner analysis because, we wouldn't be able to differentiate between a large droplet depositing a bunch of fluorescein or a number of small droplets. And I think a key point here is that we applied this to a really basic test case. And it appeared that, a drier environment enhances droplet dispersion. And what do we mean by that? It basically means that by decreasing humidity and in turn decreasing the equilibrium droplet size, the basically small background velocities present in the room become important. Essentially, once you shrink those droplets down to a sufficiently small size, then they will stay in the air long enough that they will get dispersed around the room just by basically small background velocities present, which essentially is, it's important to account for if you're trying to study, these really small aerosols. That being said, to the question earlier, yes, the equilibrium size that we produce would depend on the sort of solution that we use. And right now we're just using water and fluorescein salt. I'm not saying that it wouldn't be different if we used saliva or something else, just that it could be important to study the effect of humidity. And at least, if water and water and fluorescein salt is similar to the compound that you're trying to study, then you should account for humidity in terms of the dispersal of the droplets. But again, more experiments are needed. This is very preliminary work. I would have loved to have done this in a lot more detail, but essentially, this was a good test case to basically show that we can generate droplets, we can size droplets, and we can study where they deposit using the sort of methods introduced in the paper. And hopefully these methods can be used by somebody else to do more experiments and characterize humidity effects much more thoroughly using different starting compounds, not just water and fluorescein salt. And before we get into methods for studying particles, I just want to take a quick pause here and see, are there any sort of burning questions that I could ask or answer? Great. Okay, then I'll keep on going. Essentially, I just want to take stock here and basically say, okay, so we've sort of gone through the sort of motivation section, which is basically, why do we care about validation studies? And that's essentially because it's really difficult to know where droplets move in different environments. So we need validation studies because the equations that govern droplet motion are really complicated and they require known flows in which the droplets are being dispersed. So yes, droplets are really good to study, obviously, because they're the most relevant test case. But if we're trying to neglect terms in the equation in order to have a more simple test case for validation studies, then particles become really attractive because they don't evaporate and it makes them so much simpler. So we also want to develop methods for studying particles. So basically, now that we have a quiescent environment that I showed previously, basically the walk-in freezer, and we have fixed size particles, there's no evaporation, which is great. How do we eject particles in a repeatable way? How do we determine where they're deposited? We need a totally different set of methods for studying this, but very important for developing validation studies. So basically, there's many different ways that we could eject the particles. You kind of see the spectrum here, and this isn't a complete spectrum, because if we kept on going to, we could have a fully realistic cough, right? Like somebody actually coughing, but that's not particularly repeatable. So what we wanted to show here was sort of mechanically generated flows, beginning with sort of steady state pipe ejection, which is a well understood flow. Doesn't really have much to do with a cough, but it's well understood, and it could be used to validate studies. Versus, impulse ejection, sort of like to replicate a cough, sort of like highly transient event via an intubation trainer with realistic airways, which again is approaching a realistic cough. It isn't exactly one, but it's still interesting to study. But because we're focusing on validation methods here, we want to start with a well-characterized flow. So we're going with the steady state pipe ejection. If I have time, which I probably won't, but I can maybe go through a couple slides, I'll show the experiments that we did very quickly with the impulse ejection. So how do we go about having a steady state particle ejection? Well, basically we have particles inside this particle blaster from Levision, which basically, as we inject pressurized air, it goes through inline ionizers, and then it sort of suspends particles in this particle blaster and then carries them out through this sort of long straight pipe before being ejected into the room. And we eject particles for 30 seconds. The ejection velocity is 33 meters per second. That's somewhat arbitrary in the sense that it's a validation study. We just want to have basically something that we needed sufficiently high velocity to sort of kick particles out of the particle blaster. And it didn't, while we're generally interested in cough and sneeze type flows, we wanted to make sure that it was just something that was repeatable. Because that's the most important thing, is that we wanted to produce a well-known flow field for validation. We ejected 3 different particle sizes. So, 25 micron, 50 micron, and 200 micron, sort of spanning what we expect to be the range of like an aerosol, sort of something that would react to sort of background flows present in the room, versus a ballistic particle that would respond more to its initial velocity and then would sort of ignore these background flows as it just dropped like a cannonball to the ground. Essentially, we did some PTV on the large particles, and so they're being ejected in sort of top hat velocity profile at about the flow rate that we'd expect, or about the velocity we'd expect. Now that we're ejecting particles in sort of steady state way, we want to be able to measure how they deposit. So how we did that was that we had this series of forensic like fingerprint lifters that we set around the room in sort of known pattern. And again, why did I mention this electrostatic effect is because it was really important for these fingerprint lifters. Essentially, if we didn't charge neutralize the lifters, then no particles would deposit on them, which was really frustrating. And so essentially we had to treat them with a ionizing bar to sort of reduce the charge on them. And basically by, having an inline ionizer in the ejection process, we were able to reduce Q. And then by sort of, again, treating the sampling strips with a ionizing bar, we could reduce E, like the electric field. And then together, you can see these middle strips here in which there's sort of no effect from charge, which is what we want, because we want to neglect that, or we want other people to neglect that when they're using our data for validation purposes. Once we have the particles that deposit on these strips, we can measure or we can count the number of particles that deposited, which is great. There's more information in the paper, but basically we sort of developed this MATLAB routine to reject dust particles, and we had high accuracy when we compared to microscopy techniques. Basically, the short summary is that we have a way of ejecting particles in sort of steady state jet. We can place these sampling strips around the room, and then we can see how particles deposit on these strips to create this validation data set. So again, I mentioned we ejected 3 different particle sizes. What the sort of key here is that they all deposit in the room differently. basically the smallest particle sizes are carried through to the far wall and sort of dispersed laterally because they experience end-well effects. The middle particle sizes experience dropout throughout the trajectory, but they still sort of experience end-well effects, and the largest particles again deposit ballistically before they reach the end wall. And it really goes to show that again the particle size and the sort of how the sort of particle air mixture carries these particles and drops them out gradually is really important and really difficult to measure. But basically, again, just sort of returning to this fundamental mechanism, basically, again, we have a complex interaction between the puff and the environment that determines location of dropout, even despite the fact that we're not even, that evaporation has no effect here, right? We're ejecting solid particles. And you can see that sort of mid-range particles start to drop out earlier than both aerosol and ballistic particles. And this has been very difficult to predict a priori. Essentially, again, going to show that it's really difficult to predict where droplets go once they get ejected into a room, even a room that's very clean, very characterized, and they're solid particles, so there's no evaporation here. So how does this compare to CFD simulations? Well, a collaborator conducted some simulations for which a couple characteristics of the simulation are given here. More details are given in the paper. I'm not going to go into this in too much detail because this was the work of the collaborator, not myself, but basically it was a one-way coupled model with an Euler flow field, Lagrangian particle trajectories, and essentially they created the domain that we had inside the walk-in freezer, and then they were basically looking to see if they could compute the same concentration distribution on the floor that we did. They had two simulation cases, so basically a transient jet, which is just they eject the particles into the room for the same 30-second time that we did, basically so that there's no background. The background flow in the room as the sort of that jet circulated back around was still developing. Then they had a sort of steady state jet to see if there was a significant difference between these two cases. And basically the short answer is that yes, there was a significant difference. The steady state jet over predicted how far, especially these middle size range particles would be transported in the room, essentially showing that the transient sort of background flow buildup did matter in terms of accurately predicting how particles moved in the room. Again, showing that even the sort of like what I would definitely argue is a second order effect of the sort of background flow present just from this end wall impact, because the room is only 3.7 meters long, was significant in terms of determining how particles dispersed in the room. And again, we see that even for the quiescent case, the spread of the larger size was underpredicted. The lateral spread of the small size was also underpredicted. So essentially, even with the lack of flow obstructions, thermal gradients, even neglecting evaporation, electrostatic effects, and essentially trying to make the cases as simple as we reasonably could, albeit with end wall effects, there's still challenges in predicting particle transport. So as a short summary, we've developed methods for studying the deposition patterns of liquid droplets, the fluorescent tracer, for solid particles. And in doing so, we identified some major challenges. So basically, the transport of aerosol, so what we characterize as those particles that have high resonance times, if they were a droplet, basically that their evaporation timescale would be smaller than the sort of deposition from the height that they were ejected at. And the transport of these like small particles is highly sensitive to background flows, which is very difficult because it's very difficult to have no background flow in a well-characterized background flow. So it's really difficult, at least in our experience, to eliminate thermal gradients, electrostatic effects, and even when we count for these, the flooded particles, it's still difficult to predict. So some key takeaway messages. Basically, what I'd say is just to treat deposition studies that do not have careful treatment of boundary conditions with some skepticism, just because in our experience they were important, especially for small particle deposition patterns. And basically, we need more validation studies, and hopefully these methods kind of kickstart some work into that, where hopefully people can use these methods to study particle deposition in a more canonical way, or droplet deposition, again, if they're interested in that sort of water fluorescent mixture. And notably, this is the simplest case. So, there's obviously we need to study particle dispersal with more complex flows. And I won't go into the sort of next paper that uses this, but instead I'll leave it here, and would gladly take any questions. I see a couple in chat already that I'll dive into. Again, I'm not going to go into too much detail on the simulation side because it wasn't my work, unfortunately, but there was no coagulation considered in the simulations. The particle trajectories were considered independent one-way coupled trajectories. And it was a RANS model.
If I can ask a quick question, even though I'm not remotely involved with stuff like this. I'm wondering how much, if you do have a liquid-like particle, how much does the composition really, would you think would affect this? Like if you had maybe some surfactants or like other things that might really want to hold on to water, how would that affect your results, do you think?
I think it could be pretty significant. And that's where I really hesitate to sort of generalize any of our conclusions to anything beyond the water fluorescent salt that we studied. Just because what we experienced anyways was that just sort of given the fact that humidity does have such a big impact on the dispersal in the room, then it's like, well, clearly there's some large evaporation rate effect, right? And if that evaporation rate changes, whether it's due to the humidity change in the room or due to surfactant or other compounds present, irrespective, it's still going to be significant, right? No matter what caused it. So, and I'm not sure exactly what that impact would be. Basically, it depends on how strong the or how significant the surface tension change was, for example, if you're using surfactant.
Cool, thanks. Yeah, we do have another question in the chat. And they say, really fascinating work. I'm interested in the intubation trainer. Does it generate a realistic size distribution? And could the jet exiting from the trainer be heated to take into account warm flow as it is from exhalation?
Yeah, it's a great question. I have some slides just going through that I could really quickly go through here. Basically, this is what the intubation trainer looks like. It looks a little creepy, to be honest. But essentially, we basically blocked off the nose structure and we're just ejecting it through the mouth. What we did was that we essentially had this sort of particle trap, which is basically like a wire mesh below the bottom of the airways present in the trainer. And then as sort of the cough was ejected, it suspended those particles as it passed through the wire mesh and then out through the airways. So the intubation trainer itself sort of didn't generate the droplets. We were using solid particles that we kind of suspended as we passed air through the airways of the trainer. And yeah, with regards to the sort of heating, we did consider it. We tried different ways to heat it because it is a significant effect. Ultimately, we decided we weren't going to do that, largely because we noticed sort of other interesting effects, and we thought that it sort of complicate the story to include the sort of thermal plume effects as well. But basically, yeah, I won't go into too many details here, but I would encourage you to look at the paper and definitely reach out to me if you have any questions, because yeah, I would love to talk more about it, just ran out of time.
Cool. Joshua Harrison asks, did you model how long submicron aerosol would remain in the fluid flow of the exhaled breath before either the breath diffusing into the air or the particles exiting from the fluid flow? I hope this makes sense. An interesting talk. Thanks.
Yeah, so as far as I understand the question, I think what you're, and definitely mention if I'm not, but basically it's how long will the sort of submicron particle sort of rest in that like multi-phase puff that's being ejected. And essentially that's a really hard question to answer. It's really complicated. I think it's something that I definitely don't know for sure. And I would potentially argue that I don't know if anybody knows. It's something that's sort of up for debate because how that multi-phase jet disperses in the room is sort of a complex function of the environment it's dispersed in. Generally, that 2014 paper that I can go back to that slide potentially from Lydia Berubia gives some conditions at which they expect fallout to occur based on droplet size. So I would kind of encourage you to look more into that paper, but their group is a lot more of an expert on it than I am. But it's a great question and one that I'm not positive on.
Well, we just have one comment on the potential impact of heating. And I don't see any other questions at the moment.
Yeah, to the comment about the heating, yes, it's definitely a significant effect. I think this 2014 paper also mentions that heating is a significant effect. Basically, the reason that we didn't heat the intubation trainer cough is because we were noticing some additional effects, and we wanted to sort of separate the effects of the mouth geometry from the effects, the sort of puff dynamic effects as it entered into the room. So by kind of keeping it the same temperature as the environment, it allows us to sort of neglect some of those buoyant puff effects that would be important. But yes, for a realistic cough, definitely important. And we just want to sort of separate those two effects, kind of in the same way that we're doing right now, right? With the steady state jet, is just trying to make that equation as simple as possible for the purposes of validation.
Well, if there are no more questions, I think we can probably end it there 5 minutes early. Oh, wait, we might have one here. Are you aware of any work, I assume maybe trying to validate the imaging? Yeah, okay. So yeah, is there any work trying to validate the imaging?
Yeah, so I guess it depends on sort of what section of the flow that you're trying to validate with imaging. In terms of particle dispersion within the sort of puff, I think there is some work being done on that. I'm not positive. But I think what our challenge was anyways was just, to study dispersion on the floor to get basically images that would be high enough resolution to see the size of the particles that we were ejecting, when they're dispersed on sort of a room scale environment. It was really challenging. I think that's where we basically needed the sampling strips so that we could then take those strips and put them under a high resolution scanner in order to get the resolution to actually see the 25 micron particles. So basically, yes, I think the short answer is that I think there is a lot of work being done on imaging, of the flow itself, but of deposition. as far as I know, it's just sort of like subfield images, not like the full room at once. That's where I think you need to use something similar to what we're doing with like sampling strips or something else.
Cool. Well, if there are no more questions, I'm going to go ahead and stop the recording, and everyone check your inboxes for more of these lectures coming up in the next several months. And thank you, Eric, for a great talk. And yeah, hope to see everyone at the next lecture.
Yeah, thanks.